run through a couple of the examples from the P4 partial fractions section for you. I'd like at the end of the day, 3:30, to meet up with you all because I've got to be in hospital. The focus on this is to actually just find alternative techniques as well for the partial fractions. The reason we need partial fractions is that they allow us to integrate functions. So if I start with the first example, the 6x minus 2 all over x minus 3 and x plus 1. Now, we did a section P3 where we actually turned it into a quadratic, which is x squared. It's going to be minus 3, it's going to be minus 2x. And what we did was we tried to multiply that through, and we realised this is going to be this, so we know that we can write this in a form of ax over a quadratic. That was fine when we could divide. The partial fractions we're doing now are proper rational functions. So these are now proper, where the order on the numerator is smaller than the order of the denominator. So we're going to do, what we can do is we can say, well, this looks a bit like a fraction normally. If we deal with fractions where we've got a common denominator, I could ask you what fraction would give me, sum of two fractions would give me something that's 5 over 6. Well, I know that sixths can come from a 2 and a 3. So what I could then do is work out what a and b would be. And the way you do it is you multiply both sides by 6. And I get 5 is 3a plus 2b. We know that these must be proper, and therefore you could actually choose a and b, both of them are 1. B equals 1. And that would allow me to actually say those are the same. That's basically what we're doing here. We're doing them as separate fractions. So we're going to have 6x minus 2 all over x minus 3 and x plus 1. And that must equal some value a over the first fraction part plus fraction b over the second term. So we're actually breaking down the factors of this left-hand side, and it's important we are including all potential factors as well. A repeated factor, like an x plus 1 squared, has to be dealt with separately from the single factor x plus 1. Anyway, we've built those two up. The substitution method is you choose values that will make these sides disappear. So if we take the numerator, we're going to multiply through first of all. We multiply everything by the denominator. That does mean that we really can't say anything when x equals 3 or minus 1. When we multiply by this bottom thing, this stuff is sort of a little bit dodgy. So we get 6x minus 2. By the way, that's not needed for P3, P4. It's just a caveat of be very careful. When I multiply these two by a over x minus 3, the x minus 3's cancel, so I get a and x plus 1. Plus, do the same thing on the other one, b times x minus 3. Techniques that they're talking about, one of them, the substitution method, is if I was to choose a value that would make one of these two terms disappear, so x equals minus 1, I could chuck that into these formulae and I get minus 6 minus 2. That term has disappeared, and I get plus b times minus 4 times minus 4. So that means that b must be 2. If I do the other side, and say when x equals 3, this term disappears. We get 18 minus 2 is equal to a times 4. So 16 over 4, a must be 4. That's by using substitution. You pick values that will make one of the terms disappear. Nice. It's actually quite a nice technique for this. Apart from when you get piles of things, then you wind up building lots of simultaneous equations. The alternative method is by equating coefficients, just as we did before. Which we will do. Oh, sorry. So that was substitution. Powerful, except when you start getting multiple terms on the bottom, the numbers don't always disappear nicely. So you might wind up with simultaneous equations, which we get from this anyway. So we're taking this term, and now we multiply through, and we've got 6x minus 2 is equal to ax plus a plus bx minus 3b. Equate the coefficients. So the x term gives me 6 equals a plus b, and the number term, because I can't say anything from this one, gives me minus 2 equals a minus 3b. And now you're into solving simultaneous equations. So if I take this one away from that one, I'm going to get my 8. A's cancel, is 4b, so b equals 2. Substitute it into one of them. That's probably easiest to put it into the top one. So 6 equals a plus 2, which tells me that a must equal 4. So now we can actually rewrite this expression above, the 6x minus 2 over x minus 3, x plus 1 is equal to, and make sure you get them the right way around, the x minus 3 was over the a, under the a. So we get 4 over x minus 3 plus 2 over x plus 1. And you might ask, what's the reason for doing this? Well, it's a way that we can actually use this to integrate functions, proper functions. So we've got a proper function where p of x over q of x. And we wind up with these nice terms that you might recognize now, and you are going to wind up getting logs from it, but at least you can integrate them now. If you look at the examples that they're doing in here, they say things like, now I'm not going to do the examples they've given you because they work out as whole fractions on the top. They would say that we can use this for multiple terms when we get 7 over x minus 2, x plus 6, x plus 3, which becomes a over x minus 2, b over x plus 6, c over x over plus 3. And it is, but the fraction, they come out as whole fractions. We'll have a look at example 2 in a minute. The other thing they said about watch out, they say in there that watch out if this was squared. And that's because there are actually therefore 3 things that need to be considered as possible fractions. We've got x minus 3, the x plus 1, and although it's a bit odd, x plus 1 squared, you would be tempted to put a cx plus d. It turns out that if you've got both of the linear and the linear squared, you can actually you don't need that cx one. What they talk about there, saying that you can't just have b add on c because they're each separate terms. That's sort of equivalent to saying, right, the way to expand it. Actually, let's write that note. So they've got an example there, which is x plus 4 over x minus 1 squared, and they're saying that you cannot do a x plus 4 and say, oh, this is repeated. So x minus 1. Yeah, that's not going to work. They're also saying that you can't just do, oh, repeat that for the next term, because that's not a different factor. These sort of combine together to give you just a single factor. Now there's two approaches. There's the method we did in P3, which would be to say we've got a over x plus 4, add on a bx plus a c, all over x minus 1 squared, which would work because we've got our quadratic components with a simple fraction. And it's partly because of this that they're offering the second way, which is actually to, and I don't need to erase that, take off those. What they're actually saying is that this can be rewritten as 3 terms, one for the x plus 4, one for the linear term that's being squared, and then another one for that term being squared. Because if you actually think about it, if we wanted to convert them into this, you would multiply this by b times x minus 1, add c, and they would both be over x minus 1 squared. And these would be a different b and c to this one. These would be different, but you would get a similar expression. Okay, so you've got that technique, but you've also got this technique here, which can be nicer when we're dealing with integration. That's why they're showing us this method, is so we can do integration with it.